So in Algebra Homework 8, Problem 3, we have the group S3, the symmetric group, and we take the cyclic subgroup generated by this permutation sigma. Right? And if you look at sigma, sigma squared is 132, that 3 cycle, and sigma cubed is the identity. So the subgroup H consists of 3 elements. So we have the order of the group S3, that's 6, and the order of the subgroup H is 3. So we know immediately that by Lagrange's theorem, the number of left cosets, which is also we write as the index, is going to be the order of S3 over the order of H, which is 6 over 3 is 2. So we know there are only 2 left cosets. Okay, so there are 2 left cosets. Okay. Any questions about this so far?
Which
So
homework is that?
I'm sorry, I didn't hear you.
I said which homework it is.
It's homework 8, problem 3. So the large group is S3, the subgroup is H, and they're going to be 2 left cosets. In any case, part A is just to compute H. So we just did that. Part B is to prove H is a normal subgroup. And that means that to prove that the left coset XH equals the right coset HX for all permutations in the group S3. Now, okay. So if X is in H to begin with, then XH is equal to H is equal to HX. Because if you multiply a subgroup by an element in the subgroup, you stay inside the subgroup. So that tells us right away that EH equals HE. Of course, this is obvious because this just says multiply everything by the identity and nothing changes. Sigma H equals H sigma, and sigma squared H equals H sigma squared. So for 3 of the elements in the group, E sigma and sigma squared, we know that this condition has to be satisfied. But then we have to do the calculation for the other elements because, I mean, the group S3 is a group you should know very well. S3 consists of 6 elements. There's the identity. There's the permutation sigma, 1, 2, 3. There's the permutation sigma squared, which is 1, 3, 2. Sorry, is there a question? And then we have the 3 transpositions. I call them sometimes tau 1 is the transposition 2, 3. Tau 2 is the transposition 1, 3. And tau 3 is the transposition 1, 2. So 1, 2, 3, 4, 5, 6. These are the 6 elements of the group.
I have a question.
Go ahead.
So how do you know that tau 1 is 2, 3 and tau 2 is 1, 3 and tau 3 is 1, 2?
Oh, that's just, I'm just giving them names. I could call them, you know, Joe, Mary, and Bill. It's just a name. I mean,
when you give it to us in the exam, so how we know which number is it?
I'll define it. If I use this in notation in the exam, I'll define it. I'm not going to just say tau 1 and not tell you what tau 1 is.
Oh, okay.
Okay. But these are the permutations. And these sigma, sigma squared, tau 1, tau 2, they're just names. I could call them X, Y, Z, or anything I like. Okay. So let's compute the left coset tau 1h, or 2, 3h. So what is this? This means you take everything in h and multiply it on the left by 2, 3. So that's 2, 3 times the identity, 2, 3 times sigma, which is 1, 2, 3, and 2, 3 times sigma squared, which is 1, 3, 2. Right? These are the three elements of this coset. And then you just have to calculate them. 2, 3 times the identity, that's just 2, 3. What is the product of these two permutations? Well, it's like composition of functions. 1 goes to 2, 2 goes to 3, so 1 goes to 3. 3 goes to 1, goes to 1, so 3 goes back to 1. 2 goes to 3, 3 goes back to 2. So this is just the permutation 1, 3. And what is this? In this, 1 goes to 3, goes to 2, so 1 goes to 2. 2 goes to 1, goes to 1, so 2 just goes to 1. 3 goes to 2, goes to 3. So tau 1h consists of these three transpositions. And if you compute h tau 1, you do the calculation. This means E times 2, 3, 1, 2, 3 times 2, 3, 1, 3, 2 times 2, 3. So the identity times anything is 2, 3. This sends 1 to 1 to 2, 2 to 3 back to 1. See, 1 goes to 3, 3 goes back to 1. 2 goes to 3, goes, 1 goes to 2, 2 goes to 3, goes to 1, and 3 goes to 2, goes to 3. So this is just 1, 2, and this 1 goes to 1, goes to 3, 3 goes to 2, goes to 1. So the order doesn't matter. This set is the same as this set. So tau 1h equals h tau 1. So for this transposition, the condition on being a normal subgroup is satisfied. And you can check either by a calculation or by a different argument that tau 2h is h tau 2, and tau 3h is h tau 3. So therefore, H is a normal subgroup. An alternate proof is the following. The group S3 contains 6 elements. You have E, sigma, and sigma squared. This is H. And the other 3 elements are the 3 transpositions, tau 1, tau 2, tau 3. So, yes, question? Question? So if you take a coset, there are only 2 possibilities because cosets have no elements in common. They're either equal or they're disjoint. So if you don't have H, the other coset always has to be this. So tau 1H contains tau 1 and H tau 1 contains tau 1. So They both have to be equal to this set.
Okay, Professor, there is also the letter D. Can you do that? Where they're asking like to show that the group is abelian, or the question group is abelian.
Yeah. Well, let me finish I've only done, this is just part B. So let me do part C. So, well, part C is easy because what is the quotient group S3 mod H? It has two elements. It has H and it has the coset. Well, it doesn't really matter which one we pick, say tau 1H. These are the two
Professor,
elements.
how did you get the H?
H is what the whole problem is about H. In part A, we compute the quotient, the cyclic subgroup H. Right? This is H throughout the problem. It doesn't change.
Oh, okay.
Right? So there are only two elements in the group. And the multiplication table, H, tau 1H, H, tau 1H. This is H times H, which is H. This is H times, well, this is the identity. So this is tau 1H. This is tau 1H. And tau 1, this is tau 1 squared H. But tau 1 squared is the identity. So this is H. And it's abelian because order doesn't matter. H times tau 1 is the same as tau 1 times H. Abelian. Every group with two elements is abelian. There's nothing else it could be. Right? But that's the proof is this is the multiplication table. You look at all possible products, xy equals yx, no matter what x and y you pick. So the quotient group is abelian. Right? In fact, every group of order 2 is abelian. And this is a group of order 2. It only has two elements. Each element is a coset, but there are only two cosets.
I have a question.
Yeah, go ahead.
So for the quotation group, we have to use the
Sorry, for which
multiplication. The quotation.
You mean permutation?
Let me see.
Or quotient
No,
group?
quotation. Yeah.
Yeah, okay. For the quotient group, yes. What is your question?
So we need to use the multiplication table.
When do you use it? It
No, I
depends on
said
what
we have.
it depends on what you're trying to prove. Sometimes you need it, sometimes you don't need it. Sometimes you have a choice of using it or not using it. It depends on the question.
Oh, Professor, but
Wait.
here I don't really think you need it.
Wait for this. Someone was asking me a question. I just want to make sure that you don't need, there's nothing more you want to ask about this. Okay.
No, he was asking about like the question or the table. Is why I was saying that here I don't really think we need to do the table.
No, you don't need to.
We already, we need?
It's not necessary.
Because
there are other ways.
Yeah, because we already defined H, and now we show that it's a normal group. Since here we have like the same result of Taiwan H equal to H Taiwan.
No. No. That does not mean the quotient group is abelian. Right? That's the definition of a normal subgroup. but the quotient group could not be abelian. In many cases, it is not abelian.
Oh, I see. So the table is just like to prove that the quotient group here is abelian.
Correct.
Oh, okay, I see now. I see. Professor, can you check the homework 9 question for also?
Wait, just 1 second. So someone asked me on this to do 10 to 15. Is that correct? So I think Tamina Chaudhuri. Oh, okay. So let me do that. So this is homework 8, number 10. So we have a group G and elements X and Y in the group. And we defined what is called the commutator, which we write as square brackets around X and Y. And this is X inverse Y inverse XY. So part A is a calculation. Prove that if you take 3 elements in the group X, Y, and Z, that Z inverse times this commutator XY times Z is the same as the commutator of Z inverse XZ and Z inverse YZ. So this is a calculation. Then we compute this commutator. So we compute. If I take Z inverse XZ, comma, Z inverse YZ, what is that? That's the inverse of the first element times the inverse of the second element times the first element times the second element, right? This is the commutator of this element and this element. And of course, the basic fact in group theory is if you take the inverse of AB, that's B inverse A inverse. You go reverse backwards. So the inverse of Z inverse XZ, you go in the reverse order and take the inverse of things. So that's Z inverse, X inverse, Z inverse inverse. That's the first element. The inverse of this is Z inverse, Y inverse, Z inverse inverse. The inverse of this is Z inverse, X inverse, Z inverse inverse. And the inverse of this is Z inverse, Y inverse, Z inverse inverse. And of course, if you take the inverse of an element, that just gives you back the original element. So this is Z inverse, X inverse, Z inverse inverse is Z times Z inverse times Y inverse. Z inverse inverse is Z. Z inverse, X inverse, Z inverse inverse is Z. Z inverse, Y inverse, Z inverse inverse is Z. Now, whenever you have Z times Z inverse, that's just the identity. So you can cancel that out in these 3 different places. So what we have is Z inverse.
Professor?
Yes.
Professor? The line, the second line,
Here?
you see, the third line.
Yeah,
No,
This
the
line?
next one. No, the next one. Yeah, yeah. You say Z inverse, X inverse. After that, the value you put there, I don't really understand. How did you
so
get it?
this is Z inverse inverse, right? This element. It's the inverse of Z inverse. And the inverse of
Oh,
Z
I see.
inverse is Z.
I see now. I see. Thank you.
You get X inverse, Y inverse. Oh, this is X. And this is Y. I don't know why I wrote Y inverses there. XY times Z, which is Z inverse. And this is the commutator of XY times Z. So this element equals this element. So we do a little bit of, it's just a calculation. So this is just like high school algebra. It's just a little calculation with variables X, Y, and Z and their inverses.
It's crazy.
Okay. Yeah. Should I continue?
Yes, please.
So this is homework 8, number 10, part B. So we talk about, this is this notation, square brackets G, comma G. This is the subgroup of G generated by the set of commutators. So the set of commutators is the set of X comma Y in square brackets for all X, Y, and G, where again, this commutator of two elements is defined to be X inverse Y inverse XY. So you have to understand, what does it mean for a subset of a group to generate a subgroup? So let me just say that S be a subset of G. The subgroup generated by the set S is the smallest subgroup of G that contains S. So for example, and let's say the standard notation for this is I put S inside of brackets. So this means the subgroup of G generated by the set S. So if X is in S, then X is in the subgroup generated by S, because this is the smallest subgroup that contains S. But also if X is in S, if X is in the subgroup generated by S, then of course the inverse of X is also in S. And if X and Y are in S, then X times Y is in this subgroup, and so forth. And in fact, so this subgroup generated by S is the set of what you might call words of the form x1 plus or minus 1. That means either x1 or x1 inverse, x2, I'll just write epsilon 1, epsilon 2, x sub k, epsilon k, where epsilon k is plus or minus 1, and x1 up to x sub k are elements of S. So when you talk about the subgroup of a group generated by a set, you mean the set of all group elements that can be written in this alphabet where the letters come from S, and you include the inverses of all the elements as well. So that's the idea of a subgroup generated by a group. And we want to consider the subgroup G brackets G generated by the commutators. The set of all commutators xy, which means x inverse y inverse xy. And we want to show this is normal. So we proved that in general, H is a normal subgroup of a group G if ZHZ inverse is contained in H for all elements of the group. So this was a theorem. And so it's enough to show that G comma G is normal if for every commutator, x comma y, if you multiply it on the left by Z and on the right by Z inverse, if this is contained in this subgroup for all x, y, and Z in the group. So we just have to show that the subgroup contains every element of this form. And that's actually what we did in part A. So by part A, ZXYZ inverse is actually a commutator, Z inverse XZ and Z inverse YZ. So this is a commutator of two elements in G. So so there's a lot of algebra that goes into this, but if you work your way through the algebra, it might take, a week. It takes a long time to understand this. The conjugate of every commutator is just another commutator. So the commutator subgroup, this thing is a normal subgroup. And the last part of the problem is to show the quotient group G mod the commutator is abelian. So this means you want to show that if you take two cosets, this is one coset of this subgroup, and this is another coset. And you want to show you get the same result no matter what the order. This is the same as y, g comma g, x, g comma g. Of course, by the way you multiply cosets, this is just the coset yx, g prime, g comma gg, and this is just xy, gg. So these are equal if and only if this coset equals this coset, which means if you multiply by x inverse y inverse x y, that's equal to, if I multiply by x inverse y inverse, that cancels this. That's equal to g comma g. But this is a commutator. So xy gg is equal to this because this is an element of this subgroup. That's the proof. But again, this is, if you understand what's going on, then you are really learning some group theory.
Is this question will be in the exam?
Well, I haven't made up the exam yet, so I can't tell you what's going to be on the exam. But I would say this is much too difficult for a 2-hour exam. So I would not put anything this hard on the exam.
So we just have 2 hours?
Yeah, just like the last exam. Right, all exams are, exams are usually 1 hour and 40 minutes, a class period. But at home it's 2 hours. Let's see. Let me do on homework 9, problem 4. So we have cyclic group of order n. So I usually call that gamma sub n. So this is capital Greek letter gamma sub n, which consists of n elements generated by some element I can call a. So a squared, all the powers of a up to the n minus first power, because a to the n is the identity. That's what makes this a cyclic group. And you define a function from gamma n to gamma n by f of any element x is x to the power r, where r is an integer. And we want to prove this is a homomorphism. But gamma n is abelian. So, for example, suppose you had r equal 2. So f of x is x squared. So f of xy would be xy squared. What does x squared I squared mean? It means xy times xy, which is x times y. And because this is abelian, xy equals yx. This is x times xy times y, which is x squared y squared. And x squared is f of x, and y squared is f of y. So in the special case when r is 2, you see in front of your eyes that this is a homomorphism. Suppose we take r equal 3. So then f of xy would be xy cubed. That's xy times xy times xy. But the group is abelian. You can interchange the factors. That's x times x times x times y times y times y. That's x cubed y cubed, which is f of x times f of y. So again, you see that this is a homomorphism. And in general, for any r, f of x to y, if it's xy to the power r, if r is positive, this is xy, r times. And you can rearrange because gamma n is abelian. You have rx's followed by ry's, rx's, ry's, x to the r, y to the r. So this is f of x times f of y. And that's the proof. Right. Any questions about this? So what about the next part of this problem? So this is homework 9, number 4, part B. So we have a function from gamma 20 to gamma 20. So this is the cyclic group of order 20 defined by f of x is x squared. So what is the kernel of f? The kernel of f is all elements x in this group such that f of x is the identity. That's the definition of a kernel of any homomorphism. So this is all x in this cyclic group such that x squared is the identity. Now everything in the cyclic group is a power of a. So I can say this is all a to the k in gamma 20 such that f of a to the k, which is a to the k squared or a to the 2k, is the identity. And the order of a is 20. So a to the 2k is the identity if and only if 20 divides 2k. So this is all a to the k in gamma 20 such that k is some number between 0 and 19, and 20 divides 2k. And what numbers in this set have the property that if you multiply them by 2, you get something divisible by 20. Well, 2 times 0 is divisible by 20, and 2 times 10 is 20 is divisible by. This is all a to the k, where k equals 0 or 10. A to the 0 is the identity, or a to the 10th. So the kernel of this homomorphism has 2 elements in it, identity and a to the 10th.
Professor, could you repeat this part again?
Yeah. So gamma 20, the cyclic group, this is a squared, a cubed, up to a to the 19th. That's what this group looks like, where a to the 20th is the identity. That's the cyclic group of order 20. And the function f is f of x equals x squared. And we want to compute the kernel. The kernel means all the elements in the group such that f of x equals the identity. Or in other words, all elements x in the group such that x squared equals e. But the elements in the group, they're all powers of k. Gamma 20 is a set of all a to the k, where k runs from 0 up to 19. So we want to find all the elements a to the k in the group, where f of a to the k is the identity, which means a to the k squared is the identity, or just using the baby rules for exponents, a to the 2k is the identity. But a to a power is the identity if and only if 20 divides the power, right? A to the 20th, 20 is the smallest integer, positive integer, such that a to that integer is the identity. So we want to find all a to the k, where k is between 0 and 19, such that 20 divides 2k. And that only happens when k is 0, because 20 divides 0, and when k equals 10, because 20 divides 20. So there are 2 elements in the kernel for k equals 0 and 10. A to the 0, which is the identity, and a to the 10th.
Thank you.
And the last part of that problem, for the same group, we have the group gamma 20, the cyclic group, and the function f from this group to itself, defined by f of x is x to the power 8. So the kernel of f is all x in the group, where f of x, which is x to the 8, is the identity. Or we can say this is all a to the k, where f of a to the k, which is a to the 8k, is the identity for k between 0 and 19. But again, a to the 8k is the identity only if 20 divides 8k. So this is all a to the k, where k runs from 0 up to 19, and 20 divides 8k. Another way of saying this is 20 divides 8k if and only if 8k is congruent to 0 mod 20. And you can divide this congruence by 4, because 4 divides all these numbers, if and only if 2k is congruent to 0 mod 5. Right, just divide by 4. If and only if k is congruent to 0 mod 5. So which of the numbers from 0 to 19 are divisible by 5? So the kernel of f is equal to a to the k, where k is equal to 0, 5, 10, or 15, just the multiples of 5. Because each of these numbers raised to the 8th power gives you the identity. So this kernel has 4 elements in it. Any questions about this?
In the exam.
Well, so, you know, in the first part of the course and on the first exam, we looked at, you know, basic fundamental groups like permutation groups, matrix groups, the integers, congruence classes, congruences, and so forth. And in the second part of the course, after the first exam, we started to do group theory. So you have to understand the definitions of all the things we consider. What is a group? What is a subgroup? What is a normal subgroup? What is a homomorphism? What is a normal subgroup and a quotient group? What is Lagrange's theorem? And how do you prove Lagrange's theorem? That's a very fundamental fact. I mean, they're the basic things that are in the notes. In the beginning of this section of notes I posted on group theory. You know, the simplest the simplest groups are abelian, the easiest groups. And the simplest abelian groups are just cyclic groups, finite cyclic groups. That's what we've just been talking about. But there are a lot of interesting groups that have come up in the homeworks, like lattice points in the plane. You know, I mean, You have the XY plane from calculus, and you look at the points with integer coordinates, and they form a very nice group, and they have subgroups. And there were some problems that I did in class, I think, on Wednesday about calculating cosets for certain subgroups in the plane. Like you had the line y equals x, that's the 45-degree line. And then that's a subgroup. And the cosets are all the lines parallel to that. So all the lines with slope 1 with an integer y-intercept. I mean, that sort of thing is definitely the most important thing to know. It's like the basic theory of groups. And if you take a second semester of algebra, which we offer at Lehman periodically, the instructor will assume that you know all of this basic group theory. Question, comment? No? Okay. Well, all right. So then we'll stop for today.